Okay, being in London, for a person of my age, you have to start with the statements from either the Beatles or the Rolling Stones. And this is an interesting title, it's Start Me Up, and it was the start in 1981 when this was released, when I started at Krebsöger. So the title of the presentation is Market-Changing Products and the History of PM. I have to define what kind of PM I'm talking about. The history is about 30 years, 25, that's the anniversary, so it's a relatively young history. And you see here, I want to talk about also of powder. I call this an enabler for a PM part. I thought of giving also the example of PM high-speed steel. I was lucky that I took it out later. I had prepared it, but Ole has nearly explained what I wanted to explain. So there was sometimes you are lucky. And then I want to talk some examples, and there are different reasons why these parts have developed, and some are big contributors, some are less big contributors in tonnage, but the importance is all given. And then an outlook and a summary. Talking about what is the PM market I'm talking about, I took this picture from EPMA. We are talking in Europe in value of some 10 billion markets in value. And you see here 23% is PM structural parts. And this is what I'm going to focus on, PM structural parts, and in principle also PM iron structural parts, so rather simple. So I want to talk about iron-based parts for the automotive industry, as automotive is 80-90% of PM iron structural parts. And as a measure for the market, because of the lack of other numbers from parts-making industry and, let's say, enough reliable markets, we are used to apply the numbers we get as reports from the powder makers via the industry federations. And you see here the three regions, and it's from 1980 to 2010 or 2012. There's a lack of reliable European numbers before 1990, so Bernard maybe didn't get a good history on the numbers, so I did a kind of educated guess based on the Fachverband numbers, because there was always a certain ratio of Germany versus Europe, so I took the Fachverband numbers and extrapolated backwards to 1980. You see here the flatness of GPMA, and you see here the time 1980 to 27, just before the crisis, there was a factor of 3.2 growth in the US or in North America, 3.6 when you took 1980 as 100% for EPMA, and only 2.6 for Japan. The reason is that in Japan, this transplants, the move out of manufacturing from Japan of automotive especially started early and earlier, so there was less supply industry there. And I call this time from 80 to 27 the period of strong volume growth and related innovation. This growth is faster than the automotive markets were growing in this time. That means we had a positive ratio of substitution against competing industries. So just as an earlier remark, I will talk more from later with showing my examples from the technology, from the market pull, from the customer side, our customer side, or my former company's customer side. And but there was a strong technology push, obviously, and this only made the market pull available or happen. So there is the pressure, the development on powders, which is a technology push, and it's roughly these 30 years. We start from simple mixes and are today at the hotspots of lubricants, of new alloy systems, and hybrid powders. We have the design and the tool design and tool making processes. Paul talked about it. At the old days, we were still at the drawing board. Then the 2D CAD came, the 3D CAD, the combination to testing and simulation. And today, the CAD-CAM press integration, and so are the hot topics. Then we had the presses, from simple presses, mechanical or hydraulic presses, to the fully controlled CNC presses, also the CAD-CAM setup integration as with the tools, and electro presses is a hot topic today. And we have furnaces and atmospheres, and I also would support Paul's argument saying that the presses have more contributed to the progress, but it also, I don't think we can blame furnace makers. Also, I just remind, it's GKN cinder metals, but the sintering nearly nobody understands in the company. It was also Sinter Metallwerkrebsöl, the statement was the same. And so some companies, I think the prime focus still is pressing, and I think there's more to achieve with improvements on the furnaces than some people imagine. Okay, the easiest part for me was to collect data from the presentation from Per Lindskog from Gothenburg, because he had the keynote on the disc alloy. And I think this was a prime enabling product for parts makers to have a real good quality product. What is the target, or what is the disc alloy? It was, we heard about the lousy properties of the powders before. This was the having a homogeneous powder mix, no segregation, or let's say low segregation in a technical speaking, high compressibility and good flow. And the starting point was a kind of market pull, because as Per told, it was the French automotive industry, they asked for good powder to make high-performance parts, which was a synchronizer hub at PSA at that days. So it was a strong market pull, though the targets were more or less asked for by the OEM. And I said it's the cleanliness, the uniform distribution, the good flowability, and high compressibility. And the solution Höganäs developed, and I know there's still a kind of discussion whether this was Höganäs USA or Höganäs Sweden. I personally feel it was Höganäs Sweden, sorry guys, is diffusion bonding, and I would say then later combined with chemical bonding for the low weight elements. So the best powder is then having the two worlds of diffusion bonding and the chemical bonding. And you see in principle these three examples of alloying concepts. The top left is the free mix with the risk of segregation and so on. Then you have the full pre-alloy, which is a good solution for powder forging, because there you don't need compressibility, or not good compressibility. A 6.6 before sintering and forging is good. That would be the method of choice. And you see the combination, which is the diffusion bonding, or then with the trade name disc alloy process. And this looks like what you see on the middle color picture. You see the molybdenum is a very fine coating, the copper is the larger part, the nickel is the finer part, and the whole thing is then the combination of these alloying elements. So I think a very bold step Höganäs AB did in 1990 was to really set up and put the investments on the disc alloy plant in Sweden. It was a new manufacturing site really focusing on large scale. It is a production from the reduced iron powder in one building to final mixes. It has a high level of automation, and it's a top standard of quality and health and safety and environmental features. So this was a very strong point, and especially also the lot-to-lot variation is just top there. I think it was costly enough, but I think it has paid the price in the meantime. The optimum solution, as I just pointed out before, is the combination of diffusion alloying and chemical bonding, and showing here you see the influence of diffusion alloying. It's hard to see, but on the left is the free mix, which is then showing this reddish color of the copper, and you see the uniform distribution of the copper, or you don't see it or when you have the diffusion alloying. When you combine this with the chemical bonding, the top picture is from Per, then you see that the combined carbon over the number of pieces is rather stable, so you have no variation for the light elements. And there's a picture from Höganäs Corporation, Chris Shade and co-authors, that you have this erratic, I think it was Sidney Luke who originally did that. It's the erratic flow and less dust, as an example, and just for my favorite topics of reach, this here is absolutely necessary if you want to fulfill the requirements for a low dust, and especially when you have nickel-containing material operation. So at the end, and this is also nice at this story, the disc alloy became a kind of global standard, which also means probably that patents have ran out, and many people are now making disc alloy type powder. So you see here that the same chemical composition is named by Höganäs AB, disc alloy AB and AE, and by GK and Höganäs In Europe, it's called this way. I think the rights for the name are opposite in the US. And the Swedes call it different in the US. Then you have QMP, Pometon, and JFE having the same grade, different naming. So it has become a standard. And it started with one synchronizer hub, and then today you see it's, for instance, very popular in synchronization systems as a total. So it's a real high-performance powder. When we go to the next, I want to start with valve seats. You see here again, this picture to the right is this volume-driven market analysis. And valve seats, probably it's not showing up if you want to find them there because these are small parts. So valve seats are near net-shape rings, and it's high temperature wear resistance, high thermal conductivity. So material properties is the first driver. It's not net shape. And this is not in the time I showed, 1980 to today. It started really in 54 because this lousy Beetle engine was air-cooled and they had some aluminum blocks in there. And with the first cylinder heads, and with the first aluminum, they needed some stronger valve seat material. So Max Köhler, the grandfather of Eckhard Köhler, who is today the owner of Leichtal, was then succeeding with his company with the success of Volkswagen in the beginning, definitely. There are some others like Brico or Federal Mogul here in Coventry or in the US, in Wisconsin, or Hitachi, who are the leading valve seat companies. So here you see the function, you see the blue, bottom blue, the valve seat, the rest is the gray is aluminum. You have also the valve guide is PM, that could be also a similar story. And then it's a small part. And it's a simple part. There's nearly the whole surface is machined, either before or after being put into the aluminum block. And this is a statement from a publication of Hitachi, and I just want to, hopefully it works. Yeah. It's high wear resistance in a dry, high-temperature environment, and depends on the combustion process. It's also on the fuel you run. There are different challenges. It should have a low aggressiveness with respect to the valve. So if the valve wears more, then suddenly the valve pulls through. So then you have a problem. And then it's defined or high thermal conductivity and a low thermal expansion and a good, excellent machinability is required. And there was a statement from Hitachi that this is today now nearly 100% of the valve seat solutions by PM in Japan, and I just added it's more or less globally true. So just to give you an idea, combustion is not a combustion. You see here you have gasoline, and there was also a development over the years from leaded to unleaded. So it's a different wear situation. There's a different wear situation between intake and exhaust. You have the diesel situation. The exhaust, you have dirty diesel, which is good because it's lubricating more or less the friction materials inside of a valve train. There is the alcohol, which is okay, but then you have the natural gas and the liquid gas solutions and the hydrogen, which are really a nightmare for the materials. And so you had to improve solutions. So at the end, there are low alloyed steel solutions, which are more or less outdated, and the very high alloyed steels or high alloy materials, I should better say, they are not that popular. So what they call medium alloyed material. And when Ole has shown this perfect homogeneous structure for high-speed tool steel, then this is just the opposite. So here you tailor by making a crazy mix of copper infiltration into maybe Powderex originated tool steel, M2 or something, which was then pressed and infiltrated by copper. So you have a combination like this, which at the end gives the tailored solution in the properties. When you look at the importance of valve seat, as I said before, you will not find them in this plot because the weight is nothing. So I made a rough assumption, 60 million cars, 3 valves per cylinder, 5 cylinders, weight 0.02 kilograms. So we're talking 18,000, maybe 15,000 tons of alloyed powder. So, okay, the value is containing high alloy material. So at the end, but without a PM valve seat ring, no car would be able to move, and the new combustion engine / fuel technologies would not work. So the valve seat is a very important part as an example for the application of powder metallurgy. And I think it was a market pull. At the end, Volkswagen has said, hey, I need this, I have aluminum, what can I do? And I would say the PM parts makers always followed to the challenges of the new engines. When we talk about powder forged connecting rods, and now we are talking big tons, I think powder forged con rods in North America is the largest family of parts in consuming PM powders. Then the history, and what is the function? Okay, the function we understand. It's a net-shaped powder forging with a high fatigue strength and excellent machinability. Machinability for drilling the hole for the screw. And competitive pricing, and the weight is somewhere between 0.4 and 1 kilo. So the history, it's quite interesting. They had all started in the 80s, and they had been independently started in Japan, US, and Europe. So in Japan, Toyota started in-house development and production for a Camry engine. In Europe, there were first developments for Porsche by the competitors Zieke and Baunbrugge and Krebsöger at that time, competitors, and Thyssen. And the production of these Conrad continued by Thyssen/Krebsöger. So Krebsöger pressed the preform, and Thyssen had the large forging press, and the whole thing was more or less a nonsense. Because it was a conventional drop forge design. And later then came the Conrads for the BMW and some Jaguar and Volvo engines. In the US, there was the start by Exotic Metals. Later came the final, today's name is Metaldyne, and mainly with focus on Ford, and Federal Mogul developed with focus on GM and Chrysler. And today we can say at least 50% of the US-made Conrads are made by PM, and the main suppliers are Metaldyne and GCAN Cinder Metals. And there is limited production in Asia, mainly Korea. There is Valencia in Europe, but the know-how is from Metaldyne. There are some interesting development steps. I took some old pictures. The top picture, oops, there is a mistake now, but these are two different rods. I don't know. Apple computer versus Windows computer. So the upper Conrad showed a more PM-like structure, which was the original from Toyota. They had made a bolder step to apply PM. The lower one, which are here both, I don't know why, is the design of the Porsche. But we can be proud that Krebsöger was Formula One champion, because Niki Lauda had this Conrad in his car when he made with Porsche the Formula One championship. Today it's titanium. And then you see what was a very funny situation. It's from the publication of GCAN Cinder Metals. After this merging situation, we had three philosophies of Conrads in the same company. So there was a strong effort, which needed a couple of years, to combine the Krebsöger, Federal Mogul, I don't know, whatever philosophy, to come to a common best solution. And Metaldyne had done a strong effort to show that the superiority or equalness of the powder forged against the conventional rods. Today you find on their website a more or less similar looking design of Conrads. The material is an interesting question. You saw the extreme of the valve seats, and you had the other one in Ola's presentation on the uniformity. For good fatigue, you need uniform material. But then you have the cost pressure in Conrads. So these stupid Conrad people in PM, they make iron, copper, carbon, which is for a metallurgist a nightmare. And they are now at 3.5 copper, which is an even worse nightmare. But if you do this by fully pre-alloying, you even get it better, because you don't need the copper admix because you forge. So if you take a pre-alloyed iron 3.5 or 3 plus 0.5 admix, then you get a higher fatigue strength because of the better uniformity of the material. What is also interesting is that the race for the fatigue endurance limit is still on. So in the 80s, we were talking about a fatigue limit of 200, 250. Then today we say, okay, you have to have 350 plus, and there are developments to even push that further. I think it was a market pull first, but then later, with the features PM has developed, it became also a kind of technology push. Coming to main bearing caps, and this is somehow a personal story for me, because This was originally, a main bearing cap is building the bearing surface for a crankshaft. It's a heavy part. It's a good story for powder makers, definitely, like Conrads. And it's a combination of vertically compared pressed features, geometrical features, high fatigue strength compared to castings, ductility, good machinability also in the combination with aluminum. And you see here the application. I can flip that through, so it's the golden parts. It's not for the price, it's just to make them visible here. For a crankshaft, and it's mainly important also today in aluminum blocks. And here you see the additional geometrical functions which you do by vertical compaction and taken from a publication. And just quickly, I want to tell the story. I think it was like an explosion in this year, that the story in 1993 and 1994, and it was Mr. Main Bearing Cap, my old colleague Terry Cadle, coming from the UK via the valve seats somewhere to the US through Goetze. And he made a publication together with two guys from General Motors in Nashville at the US conference in '93. And I just show the abstract, and I just will point out some statements. The main bearing cap will be used now, more or less, was the publication, for the first time in GM 2 V6 engines, two types. This product will consume 5,000 tons of powder, relating to our powder-based statistics, which I used here. And it is the highest volume application for PM in North America at that time. And the arguments were functional advantages, that was also these geometrical features by vertical compaction, but also elimination of major investment in main bearing caps machining lines at GM. So it was this window of opportunity that there was a big expansion at the customer, and they had to decide which process they take, and Zenith at that time was prepared to offer something. And so I think if a casting company would have offered a solution, then also they would have had choice. And I think it was a similar situation with the Conrads in the US at that time. So you see here the casting solution, what they call a leaf, and you see that you have to do a lot of machining, and this was the PM solution, which was at that time. And I think this is Bernard from Metal Powder Report. In 1993-94, and that means this was the year, the part of the year award at the same year in North America and in Europe. You want to make a picture? Some statements on main bearing caps and the future, how I see it. There is an increased component properties. You have downsizing also, not just that you omit some cylinder, but also they get smaller. But the power density still gets higher. And you have the vertical compaction necessary, so it's a challenge definitely to powder and lubrication. Many more complex geometry features you could put in. But just because of the weight of the parts, there could be a challenge. I don't know whether this is possible, but there could be a challenge for aluminum MMC, because there is this strong driver. There are definitely designer people at the customers saying, how can we bring the weight down? Whether this is realistic or not, I don't know. It was parallel, I would say, a market pull and technology push. You see the co-authorship also of Terry and the GM guys. Coming to the next, that's Planetary Carrier. So we saw the material performance of the valve seats. We saw the high fatigue plus net shape and price performance competitive situation of the connecting rods. You saw this issue, technical and financial advantages for the customer for the main bearing caps. And now comes Planetary Carrier. What was there the driver? The Planetary Carrier is a 2 or 3 piece joint component. And it's a weight between, depends on the design, 0.5 kilo and 3 kilos, so something like this. And there was a publication from Ken Bird from GCAN Cinemetals. At that time, he developed that when he was at Salem plant earlier. And you see there are two possibilities. welding or cinder brazing. And the more interesting solution, obviously, is cinder brazing, because you have only one time the heat and you run through, but you have to have the whole thing under control for dimensional purpose. The welding also allows PM, non-PM combinations. So that is also happening and interesting. The large parts need very large compaction presses. Here we are talking 1,500 ton presses or so. And it's a dream part for powder producers. And the key advantage is the reduction of machining operations. And this is from a publication from GKN. And you see on the left, when you have a classical conventional solution, these are the to-be machined surfaces. And on the right is the PM answer. And this is in many cases, but also mainly in the US, the PM solution. Also some statements. Strong growth potential with the expansion of multi-step automatic transmission. They're challenged by the dual clutch transmission, but then I showed our part in dual clutch in the next example. And also here there could be an aluminum question, because it's a heavy part. So just by this, some creative people may question that. And I think it was a technology push first, because people had to be convinced that the joining process works, and the market pull later, designing more design for PM. That was the first transmission part. The second transmission part is the Classical Synchronizer Hub. And this is a complex, multi-level, high-density component, preferably sinter-hardened net shape. So I think this is something like the holy grail to make something really strong, no machining, and depending on the tolerances, and top density. And I show here something from a presentation I did in Yokohama 2 years ago. The density should be today in the range of 7.2, 7.3, and again here as an address to the powder makers, when they say 7.4 or 7.5, it's this soup cube, 1 cubic inch. Here we are talking thin walls, and all sections have to be above this agreed density, and for this example I'm showing it's 7.3. And close tolerances, sinter hardening, minimum machining. And this is an interesting example where over the history, by pulling all technology strings, this part could be realized. You see 3 curves. I know that Paul Weiss is at that time in 98 or before, he was in Birkenau, and he said we made higher density parts as shown here. This plot comes from Birkenau, so I don't know who is right. But anyhow, you see there are several features. One is that it's a hybrid alloy based on diffusion alloy. Then second, it's the lubricant development and the higher pressures because of tool steels and of modeling and simulation of tool steels. So this was the breakthrough to come to a realistic compaction pressure of 750 megapascal. So you have optimized sinter hardening and so on. And all, as I said, pulling all strings made this part available. Also the future, there's a very high growth potential for multi-step double clutch transmissions. Also obviously the manual transmissions continuing. And also there's a strong challenge on the properties because of downsizing. It was a market pull first, PSA, we saw it at Distalloy, it was technology push later. Okay, I will go quickly through an outlook. That's the transmission gears, surface densified gears. There are several examples from different companies. And where are we today? Surface densified gears are in series production as camshaft gears or mass balancer gears in engines, as an example from MIBA. Then there are surface densified gears having shown and being demonstrated the technical capability. I refer to what Höganäs has published and some companies, and in transmission test rigs, but also on the road. First projects are in different constellations, having started for a deeper evaluation and preparation of series production. And today's challenge is to find the right starting parts for a mutual win-win situation for the first tier or OEM who are making transmissions and the PM suppliers. So I would say, and you see the holy grail, you see all these gears, this will definitely push the powder consumption. And PM transmission gears have the potential to increase the PM share per car dramatically. It is still in a technology push. I don't see a market pull here. There are many more parts, examples, the synchronization sleeve, the metal membranes, the cylinder liners, and VVT parts, very important. I prepared the tool steel, Ole has shown this, and I also thought of the interconnect planes and wanted to show a video of Planze, but you can www.planze.at.com and you can see the video there. Just one look into the crystal ball as Ole has tried. We are here, what comes to the right side. And the downsizing comes, which means in America from 6 to 4, and less cylinders means less related PM parts. This is definitely a challenge. Downsizing in Europe, by the way, means from 4 to 3, or maybe 6 or 5 to 3. And there are a couple of Germans, you can keep calm. You also can go 200 or 230 with a 3-cylinder, 1.5 liter engine, which is the example of BMW. Or another one, 40 kilograms, 400 horsepower by Nissan. So the Germans still can race. Downsizing, but there are also new markets. You have the more intelligent engines, you have the exhaust emission control systems, a reduction of fuel consumption, so you have the high-speed transmissions, the electric power steering, start-stop mechanisms. So my feeling is, based on the forecast which Eric Boretsky did, that the weight per car stays stable, that at the end, downsizing and more complex engines, we will have more different higher volume components, value components. This is good news for parts makers. But probably without increasing weight per car, if not the gears come, and this is not so good news for powder makers. So I think this is a situation where we are in the industry today. The summary, I showed 7 market changers from my view. The first one, disalloy as an enabler. Then the valve seat rings, where the material was the prime driver and the properties. Powder forged was a combination of one property, the fatigue strength, plus cost competitiveness. Then the main bearing caps, a little bit the story like Conrad. Planetary Carrier, the joining is the key point. And the Synchronizer Hub, which is the most total intelligent PM part, I think, in total. And then the outlook for the structural parts. So I was thinking for another title for coming to the end, and I didn't find it with the Beatles or with the Rolling Stones, so I chose the Doors, This Is the End. And I want to acknowledge the support from my good friend Kirit Dalal of Bleistal, who told me what is the real true challenge for a valve seat. Some input from my colleagues from GCAN Powdermet, Ian and Tim, support from MIBA and from PMG. And I want to thank you for your attention. Thank you.